In this video, we're going to cover section 1.17.1.2, inhibition in enzyme catalysis. The activity of an enzyme can be affected by the introduction of species that structurally resembles the substrate and that can bind to the enzyme active site or another binding site on the enzyme. These species are known as inhibitors. So let's consider the following reaction. This scheme here is the same scheme we discussed in the previous video regarding Michaelis-Menten kinetics. The only difference now is that we're introducing two additional pathways in which the free enzyme can interact with an inhibitor to form an enzyme inhibitor complex, or the enzyme substrate complex can interact with an inhibitor to form an enzyme substrate inhibitor complex. Now we can define equilibrium constants for these two equilibria as dissociations, and those are shown as K1 and K2. So K1 is equivalent to the products of this dissociation, which would be the free enzyme and the inhibitor, all divided by the reactant, the inhibitor enzyme complex. And similarly, K2 can be defined as the enzyme substrate complex and inhibitor, product of those two terms divided by the concentration of the enzyme substrate inhibitor complex. So the question we should ask ourselves is, how does the rate of reaction differ from the non-inhibited enzyme catalysis? Well, first, we need to define the initial enzyme concentration now in terms of all the species that contain the enzyme. So as shown, the initial concentration of enzyme will be equal to the sum of the concentrations of free enzyme, enzyme involved in the enzyme inhibitor complex, the concentration of the enzyme substrate complex, as well as the concentration of the enzyme substrate inhibitor complex. Assuming the pre-equilibrium condition is applied, then we can write the following expression. And recall that the pre-equilibrium condition implies that the rate constants K1 and K minus 1 and the rate constants associated with the equilibria for EI and ESI, that these are all much greater than K2. So these equilibria are established well before we see the decay of the enzyme substrate complex to product. So the first step in our derivation is to substitute in for the concentration of the enzyme inhibitor complex and the enzyme substrate inhibitor complex using the definition that we just defined for the equilibrium constants for those two equilibria. And that's what's shown here. We can substitute in for EI and ESI using those definitions. Now what we do is we can factor out of the first two terms the concentration of E, and that's shown here. And in the second two terms, or third and fourth terms, we can factor out the concentration of the enzyme substrate complex. And that leaves us with the following expressions. And in the last step, we're going to define these bracketed terms as alpha 1 and alpha 2. Again, under the pre-equilibrium condition, the equilibrium constant describing the dissociation of the enzyme substrate complex is equivalent to Km when K minus 1 is much greater than K2. And so you can see in this expression that we're going to equate Km to the product of the enzyme and substrate concentrations divided by the concentration of the enzyme substrate complex. Also recall that Km was equivalent to this composite of rate constants. In addition, the assumption that the concentration of the enzyme substrate complex and the concentration of product is much less than the concentration of the substrate also must hold true. In this scenario, we can equate the concentration of the substrate at any point in time during the course of this reaction to the initial concentration of the substrate. So if we take these factors into account, we take this expression and we solve for the concentration of the enzyme, we're going to end up with Km multiplied by the concentration of the enzyme substrate complex, all divided by the concentration of the substrate. And then if we substitute in for that concentration of the substrate with the initial concentration of the substrate, we end up with the following expression. So our initial enzyme concentration can be written in this way. So now if we factor out the concentration of the enzyme substrate complex, we're left with a solution for the enzyme substrate concentration. Substituting this expression into the expression for the rate of product formation gives us the following. So recall the rate of product formation will be equal to K2 times the concentration of the enzyme substrate complex. We now have solved for that with respect to the initial concentrations of enzyme and substrate, as well as these two new variables, alpha 1 and alpha 2, and we're left with the following nonlinear expression. Now, like we saw from Michaelis-Menten kinetics, the effect of inhibition can also be observed in a Lineweaver-Burk plot of the following form, where again, we're going to be plotting the inverse of the initial rate against the inverse of the initial substrate concentration. But now the main difference is that in the slope term, we have alpha 1, and in the y-intercept, we have alpha 2. And again, alpha 1 is equal to 1 plus the inhibitor concentration over the equilibrium constant for the dissociation of the enzyme inhibitor complex, whereas alpha 2 is equal to 1 plus the inhibitor concentration divided by the dissociation equilibrium constant for the enzyme substrate inhibitor complex. So when we carry out these types of experiments, it's really important that we run the experiment in the presence of the inhibitor, but also run the experiment in the absence of the inhibitor. Because what we need to do first from the uninhibited reaction is determine what Km and Vmax are. And then when you run the inhibited reaction, that allows you to determine by comparing the slopes what alpha 1 is, and by comparing the y-intercepts what alpha 2 is. So that's summarized in this paragraph here, that for this variation of the Michaelis-Menten mechanism to be consistent with experiment, a good linear fit to the experimental data will be observed for a plot of the inverse of the initial rate against the inverse of the initial concentration of substrate if there is a strong association between these two variables. And as I just mentioned, the y-intercept and slope of the linear fit provide a measure of K1 and K2 when compared with the uninhibited system. The latter must be examined to determine Vmax and Km. Now let's look at three different types of inhibition in enzyme catalysis. Each of these display a different type of kinetic behavior. Three types are known as competitive inhibition, uncompetitive inhibition, and mixed inhibition. In competitive inhibition, the inhibitor structurally resembles the substrate and occupies the enzyme active site. Once bound to the active site, the inhibitor is non-reactive and the enzyme becomes inactive. So when we look at the Lineweaver-Burk plot for this particular type of inhibition, we observe that alpha 1 is greater than 1 and alpha 2 is approximately equal to 1. Now what this means is that we're comparing the slopes of the inhibited to uninhibited reactions. So in this particular case, we're going to see an increase in the slope of the inhibited reaction by a factor of alpha 1 compared to the uninhibited reaction. However, in this type of inhibition, the y-intercept will not change. That is, we're going to see a similar y-intercept for the inhibited and uninhibited cases. This type of inhibition is shown in the diagram below, where the green line represents the uninhibited reaction, the reaction that takes place without the presence of an inhibitor, and the magenta line represents the reaction in the presence of the inhibitor. So you can see from our Lineweaver-Burke plot that there's a difference in the slope between these two lines, but their y-intercepts are equivalent. And so this is a good example of what competitive inhibition would look like when plotting the data for this type of system. In general, competitive inhibition has been used in drug design for antiviral, antibacterial, and anti-tumor applications. These drugs are molecules that serve as competitive inhibitors for enzymes required for viral, bacterial, or cellular replication. A second type of inhibition is uncompetitive inhibition. In this type of inhibition, the inhibitor binds to an allosteric site on the enzyme if the substrate is already bound. An allosteric site is a site different from the active site where the substrate normally would bind. When we look at the Lineweaver-Burke plots for this type of inhibition, we observe a similar slope, that is, alpha 1 will be equal to 1, but alpha 2 is going to be greater than 1. So compared to the uninhibited case, where alpha 1 and alpha 2 both equal 1, the slope of the Lineweaver-Burke plot will not change, but the y-intercept will increase by a factor of alpha 2. So this means that in this particular type of inhibition, the inhibitor will not interact very well with the free enzyme, but will interact more strongly with the enzyme substrate complex. This is why we see an effect on the y-intercept, but not an effect on the slope. So shown below in our diagram, the slopes are equivalent, but the y-intercepts are quite different. And this is what we would expect for this type of inhibition. Uncompetitive inhibition has been observed in cancer mechanisms and membrane transport. Our third type of inhibition is referred to as mixed inhibition. In this type of inhibition, the inhibitor binds to an allosteric site on the enzyme, whether or not the enzyme has already bound substrate. So in this type of inhibition, compared with the uninhibited case, we see both an increase in the slope and the y-intercept by factors of alpha 1 and alpha 2, respectively. So we can see from our diagram below that we would expect to see a difference in the slope. That is, you can see that the slope is increasing in the inhibited case relative to the uninhibited case. In addition, we see an increase in the y-intercept for the inhibited reaction as opposed to the uninhibited reaction. Also being presented in this diagram is a special case of mixed inhibition where K1 and K2 equal one another. That is, alpha 1 equals alpha 2. In this case, the x-intercepts for the inhibited and uninhibited cases will intersect. And so this is a special case of mixed inhibition. So those are the three types of inhibition that we typically observe for enzyme catalysis. And we need to pay particular attention to how the slope and the y-intercepts change or don't change when we compare the inhibited reaction to the uninhibited reaction. So if you have any questions about inhibition in enzyme catalysis, by all means, send me an email. Thank you.